Okay, let's see if we can walk through solving this first order differential equation. Looking at the way the problem is presented to us, we should feel like it has an exact form to it. So typically when we see a quantity dx plus a quantity dy equaling 0, that strikes us as a potentially exact equation. We do need to verify though, so I'm just going to go ahead and call this first quantity m, the second quantity n. And the way we verify that the equation is in fact exact is through calculating two partial derivatives. First, we'll look at the partial derivative of m taken with respect to y. Then we'll compare that with the partial of n taken with respect to x. If these two partial derivatives are equal, then the equation is exact and we'll push forward. If they're not equal, we'll actually need to find a special integrating factor to turn it into an exact equation. So let's go ahead and calculate these partials. The partial derivative of 27xy squared taken with respect to y means that we treat x as constant. So that would give us 54xy, since we're really just applying the power rule to the derivative of y squared and timesing that result of 2y by the 27x. The partial derivative of 8y cubed with respect to y should feel kind of more normal. That's just going to be 24y squared through the power rule. Moving on to n, we'll take the partial derivatives of these terms now with respect to x. So just watch out for what variable is being used for the derivative versus what variable is constant. So the derivative of 18x squared y with respect to x would be 36xy. Because again, we're just using the power rule to differentiate x squared and get 2x. And we times that by the 18y that are viewed as constant multiples to that term. When we differentiate 12xy squared with respect to x, we will just get 12y squared, since the derivative of x is 1 and 12y squared is viewed as a constant multiple. So of course it's pretty easy for us to see now that these two partial derivatives are not equal, so the equation is not exact. So this will be a fairly long problem. It means we need to move into finding a special integrating factor. So I'm going to pause and find a good formula sheet to remind us of that. Okay, so here's a little reminder of the process we'll use. Since we just showed that the equation is not exact or inexact, we are going to see if we can find an integrating factor. And we'll start by considering this calculation. We'll go ahead and work this out. And if that becomes a function of just x, we'll be able to find our integrating factor by taking e to the integral of that quantity. So again, I'm going to just start going back with this part here. So let's consider the partial derivative of m taken with respect to y minus the partial derivative of n taken with respect to x all over, I think it was n. Let me just double check that. Good, all over n. So we're just going to walk through that. And now we'll start plugging in our values. So in our case, let's see here, we already found dm dy, that's all the part I have in green. So I'm going to plug in my 54xy plus 24y squared. From that I'll be subtracting dn dx, which is this piece here in red. So I'll be subtracting 36xy plus 12y squared. And then we'll be dividing it by the original n, which at the beginning was given to us as 18x squared y plus 12xy squared. Right now that looks like a bit of a mess, but we're going to go ahead and clean up a bit, hoping that it can simplify to just a function of x. So let's see if we can try. Alright, so just cleaning up a little bit in the numerator, we can see distributing the negative sign, we're going to have a 54xy minus a 36xy, which sounds like 18xy. And then similarly distributing the negative to the 12y squared, I'll be combining the 24y squared with a negative 12y squared to get just 12y squared. And then in the denominator, we've still got the original 18x squared y plus 12xy squared. At first glance, it might almost seem like everything's canceling. Just be a little careful with the simplifying. If we were to look for a common factor, that may be helpful. But if we take a moment and consider how the numerator and denominator are related, it seems like the only difference is the denominator has an extra factor of x. So rather than going crazy with factoring, I'm simply going to factor the x out of the denominator. And when we do that, that x goes away. So we have 18xy plus 12y squared. So it looks like this is simplified now to just 1 over x. So the 18xy plus 12y squared is common to the numerator and the denominator. So because this is a function of just x, we can use this to find our integrating factor. And I'll write down a reminder of that formula that we saw a moment ago. So we're going to go ahead and use that to find the integrating factor. Okay, so we've found integrating factors for other types of differential equations, but let me go ahead and go back to that summary. Basically what we're doing now is, since we found that the partial derivatives over n simplified to 1 over x, we're now going to calculate our integrating factor as e to the integral of what we just found. So in our case, I'm going to be grabbing this 1 over x and plugging it in and proceeding from there to find our integrating factor. So we know the integral of 1 over x is ln of x, and e to the ln of x should give us just x. So that's a pretty friendly looking integrating factor. An integrating factor, as we've seen in other types of differential equations, now gets multiplied to the original differential equation. At that point in this problem, it will be exact. I'm going to leave it to you to verify just so this video doesn't get even longer. But then we'll go ahead and solve it as an exact equation. So I'm just going to make a bit more space. Alright, so to save a little time, I just rewrote the original differential equation we had started with. All I'd like to show now is timesing this whole equation through by this integrating factor we had just found. So if it's alright with you all, I'm basically just going to bump up the exponent on x for every term. So make sure that goes alright here. So my 27xy squared would become 27x squared y squared. My 8y cubed would become 8xy cubed. My 18x squared y would change now to an 18x cubed y. Better just erase that. 18x cubed y. And my 12xy squared becomes 12x squared y squared. So every term was multiplied by that integrating factor. As I mentioned, if you recalculated your partial derivatives, now they would be equal to each other. You can feel free to pause and verify that for yourself. I'm going to go ahead and push into the solving process, because that's what we probably want to emphasize. So once we found that integrating factor, you can see this little note here that we're going to proceed with this problem now as an exact. And the process for solving exact equations can be written lots of different ways, but the strategy we've used is basically we're going to show integrating m with respect to x, and we'll show integrating n with respect to y, and then we'll be comparing those values to form our final solution. So let's go ahead and do what we just said we were going to do in terms of solving this as an exact equation. So this term, this first quantity here, this is our m, and we're going to begin by integrating m with respect to x. And then if that goes well, we'll go ahead and integrate n with respect to y, and then we'll step back and just compare the two solutions. So walking through the integral of m, that means we're going to be integrating 27x squared y squared plus 8xy cubed. With respect to x, that's pretty friendly, so that should give us 27x cubed y squared over 3. Using our power rule for integration, plus 8x squared y cubed over 2, which we can simplify, and maybe I'll go ahead and do that real quick, to 9 x cubed y squared plus 4x squared y cubed. So there could be some additional function just of y attached to that piece, so we'll keep an eye out for that. But let's go ahead and calculate the integral of n dy. So that means we'll be integrating our 18x cubed y and our 12x squared y squared with respect to y. So that first term should become 18x cubed y squared over 2 through our power rule. Again, notice I'm just integrating with respect to y, so that's our emphasis. The next term, 12x squared y squared, would become 12x squared y cubed over 3. And if we reduce that down, we get 9x cubed y squared added with 4x squared y cubed. And it's at this point that I'm just going to kind of take a step back and compare the solutions that we found by integrating m dx and n dy. So what are your observations about these solutions? I think they look identical, right? So that means that there is no additional function of y on this first piece, and there's no additional function of x on the second piece. So when we state our solution, it's stated implicitly. So to leave our final solution, I'm going to set what we just found through integration equal to some constant c. So our final solution can be expressed as 9x cubed y squared plus 4x squared y cubed is equal to c. And that should be it. I'll leave it to you if you'd like to verify that that solution is good. Hopefully that helps.